first of all, are there any questions about anything on the homework assignment? Let's start on the homework assignment. Okay. How many people have gotten started on it? Okay, and how many people have not gotten started on it? Okay. People who haven't gotten started on it haven't gotten started coming to class. So anyway, this is good. Any questions about the assignment? Anything to discuss about rules, policies, anything going on? Okay. So today my plan for today is I want to talk more about correlation, finish that section up that we had talked about, and then go through a little bit about one of the problems on the assignment has to do with using linear regression. And I haven't taught that, and I'll really teach that for real later in the semester. But I do want to spend a little time talking about it just to make sure everyone's on board. The other thing, just to mention, I assume everybody knows that there is a quiz every class and that you have to do it. Who here has figured out that we have a quiz every day and they know how to do it? Okay. Are there any technical issues with that? Anything I should know about? Yeah? It doesn't access class. What does that mean?
It means that you remember previous sessions I about and your swap class by the lecture office into that position.
Wait, okay, this has nothing to do with the quiz. Okay, you're saying I want to register and there's some technical issue that applies to me. Okay, talk to me afterwards. Okay. Any questions about the quiz or anything else logistical? Okay, good. Okay, so let's talk a little bit more about correlation. Last class we defined what various correlation statistics are, and when there's a correlation found between two variables, that means that there is some kind of a statistically significant relationship between them. Okay, but of course the famous thing is that correlation does not mean causation. And one reason this is obvious is that a correlation is symmetric, right? The correlation of A with B is the same as the correlation with B with A. So it can't be that A causes B and B causes A. Okay? But it's often the case that people itch to say that when you see a high correlation, one of the things must explain the other. And, people often get the correlations wrong, the direction of causation wrong. Again, one example I like to say is, if you take a look at the precincts in a city and you measure their crime rate, okay, and at each place, and you measure the number of police they have at each place, you will probably have more police where there is more crime, right? Now, is it the police that cause the crime, or is it the crime that causes the police? Probably, to me, I sort of would guess it's probably more likely that the crime causes the police, okay? But that's still kind of a made-up, claim, and that I work a lot with social scientists, and social scientists worry very much about causality, okay, trying to prove that one thing caused another thing. And they are remarkably good when you talk to a social scientist. If I were to say something like, the crime caused the police, they will be very good at telling me, no, the police could have caused the crime could have caused the police, they could be independent, they could be. So actually determining that there really is a correlation is, a causation relationship is different. Correlation is a statistical observation. Causation is some kind of claim about how the world works. I like this cartoon the best, okay? I used to think that correlation implied causation, okay? That I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe, okay? The well, maybe means that they know now that correlation does not mean causation, okay? Any questions about that? So what is the situation when you have two variables that are, a question, yes?
So if there's a correlation value between two variables, does that mean that one has to cause the other or the other has to cause the other?
So what are the possibilities if you have a correlation between two things? It could be that A causes B. It could be B causes A. It could be that there is some some C that causes both A and B. I think the example downstairs. You have, does selling ice cream sales are going to be correlated with sunburn, right? On days when ice cream sales are high, okay, the sunburn is also going to be high, right? Now, is it the ice cream that's causing the sunburn? Is it the sunburn that's causing the ice cream? Or is there some other phenomena, like the sun, that is causing both of them? Okay? So that would be a situation for C. Okay? There are also such things as spurious correlations. One famous example of this is that, people want to know if, you could make a lot of money if you knew the stock market was going to be good or bad next year, okay? And so someone went ahead and took a whole database of time series from the United Nations and correlated them with the stock market to say whether or not the stock market would go up or down that year. And they found that the best prediction of whether the U.S. stock market would go up or down was the butter production in Bangladesh. You can Google butter production in Bangladesh. Now, does butter production, if they make more butter in Bangladesh, is that going to cause stocks to go up? Doesn't look like it should be. It looks like this is maybe just a spurious correlation, okay? Remember, if you have a statistical significance and you say that there's less than a 1 in 20 chance that a 95 out of 100 chance that this correlation is real. Okay? What does that mean? That means that there's a 5% chance that the correlation isn't real, right? And basically the moment that they discovered that butter production in Bangladesh predicted the fate of the stock market the last 30 years, it stopped working. And why is that? Because it was never really working. There was no causal relationship there. You have enough time series you're going to correlate with. Okay, one of them has to be the best. Okay? Any questions about that? So it is important not to overascribe it. And like I say, I have been impressed when I meet a good social scientist, how I'll get into discussions with them and I'll say, oh, this must cause that. And they'll say, well, they know not to say this causes that. Okay? We don't naturally think that way, but that's actually an interesting one. Any questions? And this was a graph I kind of liked when we were talking about sunscreen. This measures the amount of skin cancer. I think every dot represents a state, okay, in the United States. And it measures the number of deaths due to skin cancer as a function of the latitude, okay? What would we expect? We would expect states closer to the border, the equator, presumably to have more skin cancer because they get more sun. Right? And that's kind of what you end up getting with a graph like this. Any questions? Okay. Now, one aspect of correlation that is important is that that there are often kind of cycles in data that is a time series data. Your stock data is a time series data, right? At least part of it. You know the price as a function of time, right? It's making some kind of a graph. Now, many, what you call it, time series show some kind of cycle in what's, in its behavior, okay? So what kind of cycles would you have? Let's say you talk about the amount of money sales that's going on with a store. Do we expect that there is some level of periodicity in here? Okay? Do we think that there is a 7-day cycle, for example, in how much sales a store is likely to get? Why would there be a 7-day cycle in sales at a store? Yeah? Right, if people shop on weekends, what do we think that that sales should look like? They should presumably be bunk, 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 bloop, bloop, bunk, 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 bloop, bloop. Does everybody see that? Every 7 days it would repeat. What other natural explanations are there for cycles in sales data? Yeah? People get paid. Well, okay, so you're saying people get paid on Friday. So that would be okay. In general, in the United States, people get, I think I get paid on a Wednesday. But it turns out that I think that most people, I get paid every other Wednesday. And most people, I think that you're right that historically people get paid on Fridays. And if people get paid every other Friday, which I think there usually is often a 2-week cycle, you might imagine there's also a 14-day cycle. There's a separate phenomena that every 2 weeks people get their money, and if it's a week where people get their money, they blow it quickly, right? So that might be a 14-day cycle. Are there any other cycles you would expect in sales data? Yeah? So festivals, there are presumably shopping days, and in the United States, the big shopping season is Christmas, okay? And so yes, you expect that businesses in December are going to have many businesses will have their sales go up in December. And maybe, in the summer people have better things to do, and so shopping drops, okay? So you would expect that there's going to be a yearly cycle here, right? Are there any other cycles that might come up in businesses? Okay. I said 4 times 365 days. Every 4 years there's a leap day. That might be if you looked at, let's say, monthly sales. I could kind of believe that every, 36, 4 times 12, 48 months, there is probably more business in February than there is in the other Februaries because they have an extra day, right? So there's going to be all kinds of cycles in any kind of a sales series, okay? And how would you detect if a data series has a cycle in it, okay? One way to do it is use correlation analysis, but correlate a time series with itself, okay? So if I took a time series, like today's sales, and I correlate it with the sales 7 days ago, okay? That is a shift of 7 days. That's what I mean by a lag of K. K of K would be 7. If I observe a unusual correlation after 7 days, that is a sign of a bigger cycle. Is that clear, or does that need a better example here? Again, what is the idea here? Suppose I took my, this is 1, 2, 3, 4, 5, let's say 6, 7, something like that. If I now take this time series and I shift it over 7 places, what's going to happen? This time series is going to look something like this. Does everybody see that? Now, the range that I can correlate it over is not if there were n points originally. If I correlate a time series with its shift leg k, I have n minus k points in common. Does everybody see that? The value of the time series gets shorter. The length of the time series gets shorter. But there is a correlation, but I can compute the correlation. And if there is a high correlation, that is a sign of a cyclic relationship. Any questions about that? Okay.
You can remove error.
Can I remove what?
We can remove error in this.
Errors, E-R-R-O-S?
Yes.
Well, okay, when you say remove errors, what does it mean to remove errors here? Okay, here we've got one time series. By leg k correlation, I'm going to be saying for a particular k, what is the correlation between the original series and the shift? Now, there is going to be you said errors. I probably wouldn't say errors. I would be saying variance. Okay? What factors will affect how many sales there are on a particular day that have nothing to do with the day of the week or anything like that? Yeah?
When it was one cycle or two cycles repeatedly, more than, you can't do that. This is this normal cycle. I can do this. We can do this example for correlation.
Okay. What our basic principle here, I'm not sure if we're saying the same thing or not, okay? If I take my series and I shift it and I correlate it, okay? If I get a high correlation, that corresponds to a likely cycle of that period. And again, the correlation will be more meaningful the longer it is. Here I only had 2 periods. I may not believe that there's a 7-day period. But if I had a 2-year time series and I shift it by 7 and I see a pretty good correlation, that is a sign that there is a real cycle here. Okay? Now I heard the word error, which may not be what it is. I would say variance is what I'm talking about. On a certain day, you wouldn't expect a perfect correlation. You would expect that on some days, the football team, on Super Bowl Sunday, everybody's watching the game and they're not, they're not going to the stores like they should be. Or maybe if it's rainy or something like that. But again, a correlation is interesting. So we say a correlation of a series with itself we define as an autocorrelation. And, what is kind of should be clear is that every time series has something that we would call it for every time series there is something defined called an autocorrelation function. And what does that mean? For every possible leg, we compute the correlation between the time series and the leg of it, period k. Okay? And we're going to get a function that is something like this. As a function of the lag, what is the strength of the autocorrelation? Okay? And by looking at this full spectrum of autocorrelation values, we can tease out cycles. Possible cycles are going to be, measured by unusually large autocorrelations, either positive or negative. There is implicit in this a statistical significance thing. Every one of these autocorrelations, as we slide one of them over there, the larger the lag, the shorter the sequence in common between the two of them is. So we would expect that as for larger and larger lags, we have fewer and fewer points in our autocorrelation. But and that might affect our notion of significance or how interesting it is. But basically there is going to be set of bars that with these things like these red lines, where beyond it the correlation is unusually, an autocorrelation of that strength is unusually likely to occur, and that makes for an interesting cycle. Any questions? Yeah.
So based off this image, it's saying there's maybe about 3 interesting cycles within.
If I look at this, there seem to be 3 interesting cycles, maybe, and the first one is a -1 with the previous one, right? It says that, I don't know what this is the number of passengers traveling in a month. If this is true, what does a leg 1 autocorrelation mean? Let's think about it. Is there a leg 1? What's a leg 1 autocorrelation mean? It means how much is today a function of what happened yesterday, right? Do we think that there's going to be a strong leg 1 correlation in sales? I would probably say generally yes. Okay, if a business is healthy, if it gets sales today, it's going to get sales tomorrow. If a business is doing badly, if it gets sales today, it doesn't get sales today, it's not going to get sales tomorrow, right? So a leg 1 is kind of about predicting today's sales using yesterday's sales. And again, this is about, I don't know what data this is from. Okay, so it's undoubtedly not from this. I just probably did random pictures. But what did this mean? It would mean that if yesterday was a good day in this function, today is going to be a bad day. Okay? You could imagine something like that happening. You could imagine that sometimes happens. Okay? And it says also that there's a corrective effect that 2 days from now, if today is going to be inversely correlated with yesterday, what is it going to be 2 days before? Okay? If today, suppose every day, suppose the autocorrelation was -1, so it was a really strong thing. What would that function look like? It would be a zigzag going up and down, right? Now, the lag 1 autocorrelation would be -1. What would the lag 2 autocorrelation be if you had a zigzag function? Does everybody see that it's 1? That's also strong, right? Is that a different phenomena, or is that explained by the first one? Explained by the first one. So we would kind of expect that if we have a strong correlation, let's say, of period 7, we would also have a correlation of period 14, 21, all multiples of that. Does everybody see that? Okay, so in interpreting these kind of things, you have to, take that in mind. Any questions? Now, what is an implication of autocorrelation? Okay, that people don't think about it as much when you're building models. Okay? Suppose I were to ask you to predict, build a model. I said I want to predict sales, and I have this feature data. Okay? I'll have sales, and one thing that is in your data set that people sometimes forget is a possibility for their feature are previous values of the function. Let me try to say that again. What data might a store have about sales that would be interesting? If I wanted to predict today's sales, you might imagine I'd have a challenge where I'd have information about the weather, and I'd have information about competing activities or other features like that. The truth is, if you want to predict sales, one of the strongest features is going to be the sales 7 days ago, or 1 day ago, or a year ago, okay? And so there's a class of models you would make that people would call autoregressive models, which are models that basically take older values of the time series into account. Does everybody kind of get that idea? That if you wanted to predict the time series, if there is a strong autocorrelation with some previous point, that should be a feature in any model to try to predict the new value. Any questions? And that sometimes people are somehow reluctant to take advantage of. Okay, any questions? Yes?
Excuse me, I would like to say that, I can see the significant positive correlation in 7 and 14, but there is nothing in 21 as you said.
Okay, well, in this case, God knows where I stole this from the net. This is not a sales thing. This is something, it has to do with mort diff. My guess is mort probably has to do with dying and differences and, so I have no idea what this is about. So don't read anything into this time series. This is just decoration. Okay? Any questions? Okay, fair enough. Now, how do you compute this autocorrelation function? What is the time complexity of computing the lag 7 correlation, okay, of an endpoint time series, autocorrelation? If I have endpoints and I want to compute the autocorrelation between a time series and its lag 7 days, what's the complexity of that? O of n. Why is that? Because what did we do in computing an autocorrelation? We took as I recall, it was the sum of, okay, we had to compute the mean of the first time series. We had to compute the mean of the second thing. We then had to go through every one of the points and subtract off what its residuals were, square them and multiply them and add them. That was order n, right? So to compute the lag k correlation for any particular k takes linear time. If I want to compute this full function for all endpoints, all n possible lags, that means I'm doing the same thing n times. It should be a quadratic time computation. Does everybody see that? Now there's this magic algorithm called the fast Fourier transform that it turns out can compute this whole autocorrelation function in n log n. If you know about Fourier transforms, that's good. We're not going to talk too much about here. But what is it that people know? What does a Fourier transform do? People, I'm sure, who here has heard of Fourier transforms? Who here knows what they do? Few people. What does it do?
It takes a given function and converts it into a set of sign and code.
Okay, it takes the stereotype, the one-line answer from ChatGPT is a Fourier transform takes a function and expresses it as the sum of sine waves of different frequencies. Have people heard that definition before? May not know where it comes from or how it does it. But isn't that kind of what we want the autocorrelation to do? What is an autocorrelation for a week being? We have something of a world where sales are going to go up and down every week, right? Does that look a little bit like a sine-like wave? Okay. And if we think about periods of different frequencies, every week, every month, every year, okay? So it should be there's some cosmic connection between breaking things into sine waves and computing autocorrelation functions. And that, I think, is semi-believable and is interesting to know about. Any questions about autocorrelations and autoregressive models and why they might be a useful thing? Okay? Any questions? Okay, now we talked about causality. People are very interested in causality. Okay, I find a correlation. Okay, I can find whether it's statistically meaningful, that's significance testing. What I'd really like to do is if I saw a correlation, is there a test where I can say, damn it, this did, not only are they correlated, but this did cause that, okay? And so there is this field of causality testing that, is, some people like it better than others, okay? But you'd like to be able to try to figure out, is something that causes something else? And one example of a statistic test that tries to get at that idea is something called Granger causality testing, okay? We say that Y, Granger causes X. If there is a greater correlation between Y and X, if there is a time lag. Okay, if I have two time series, if I'm going to say this caused this, A caused B, A should happen before B happens. Okay? It's hard for A to cause B if A happened after B happened. So the argument or the basic idea behind this kind of causality testing would be if you measure the correlation between two variables and the correlation strengthens if you shift the time series, then that is some evidence that A causes B. Does that have some level of plausibility? Okay. Now you got to assume you're measuring it on a time scale where you can see the difference in cause and effect, right? If something happens so quick that there really is not if you're collecting data every week, and the effect of it is that at one point somebody punched somebody and walked away. You didn't see the punch, right? Because you only saw the result that after a week the guy was lying on the floor, right? But so the idea of Granger causality is if they get a stronger correlation with a lag, that's evidence that there's a causal relation. It doesn't mean that there's necessarily a direct causal relation. It could be that A causes B and B causes C. Would we see a correlation between A and B if we did that? Yes. Would we see a lag between A and B if we did this? Yes. So there's nothing in this idea that is going to detect, imply that it is a direct or the direct cause of something. Okay? And sometimes there may even be a mix of direct and indirect causes. Any questions about that? Yeah.
How do we know the lag that we have to use so that we find a correlation?
Okay, so how do you know what lag you could do? Well, I would argue that probably what Granger causality does is it computes the autocorrelation function. You compute the full autocorrelation function, you have the correlation for every possible lag, right? And now there's a question of, do I see something strong enough in one of these to convince me? Okay? That's kind of, I guess, the idea of how I would answer that question. I would say that gets us into an interesting idea, though, that we'll talk about later. If you ask what is the significance of doing something, if, let's say, we said Granger causality said that if there is a greater correlation with a time lag, that suggests, we've got a causal relationship. What happens if I have a time series with 1,000,000 points? I do compute the autocorrelation. I am computing 1,000,000 different lags. Does everybody agree? Suppose one of them lights up as being a little bit bigger than my original correlation. Do I believe that that's a proof of causality? I had 1,000,000 chances There's certainly in a world where there's some variance in what, there's some degree of noise or uncertainty or variance or, if I have too many different hypotheses that I'm testing at the same time, it's easy for some of them to come true just by chance, right? So if you're going to try to do this statistic, yes, you can try a lot of different lags, but part of the statistical rigor here is going to be saying, okay, I see this improved level of correlation, but I tried 100 different lags. Is this improvement enough to really excite me? Okay? And we'll talk about those kind of issues later when we talk about hypothesis testing. But this gets into issues of, has anyone here ever heard of the Bonferroni correction? Okay, we'll talk about that later. But that's kind of an issue that would come up with that kind of fishing expedition. Any questions? Okay, good. Okay, what I'd like to now talk about, just for as maybe the last mathematical preliminary for what we're going to do in here, I want to talk about logarithms. Okay, now I usually teach either this course or an algorithms course. Okay, has anybody ever seen my algorithms book? A couple people. Great book, right? So, yeah. But in my algorithms book, I give several reasons for what a logarithm, how logarithms are used. And I'm going to show you about 3 reasons here why logarithms are important in data science, none of which are the ones that came up in the algorithms book. So logarithms remain an important thing. We need to understand it. What is a logarithm? We say that y is the log base b of x if b to the x, y is equal to x. So what is the logarithm? The logarithm is the power that you have to raise b to get x. Okay? Everybody, let's say that one more. I know you've seen this before, but let's just put this back in your head. Y equals log base b of x is saying the same thing. This is just a definition that b raised to the power of y is x. Okay? Now, when you raise something, a number to a power, it grows big very fast, right? You raise the power a little bit, the number gets much bigger. The exponent, okay, the log function grows slowly, okay? That's one thing that you see and why you care about it in an algorithms course, okay? But basically, the log function is the inverse exponential function, okay? Any questions about that? Okay, why in data science will we care about logs? One reason is that quite often in here, we're going to be multiplying chains of probabilities. Okay? If you have a conditional probability, it's the probability of this times the probability of that, the probability of that. A probability is a small number. It is between 0 and 1. What happens when you multiply 2 probabilities? You get a smaller number, okay? And it rapidly becomes infinitely small, and you get a finite word length, you get all kinds of numerical problems. Now there is a relationship between multiplication and addition with respect to logs. The product of a bunch of numbers, okay, is the same as, okay, b to the sum of the logs of that probability base b. Okay? What do we know? We know that the log, basically, what is the log of x times y? We know that is the log, what? Log x plus log y. Okay? Now what does that mean? This means that if I want to compute, have a long multiplied things, I can reduce it to the sum of logs, right? Summing is numerically stable. Computing the logarithm of something is sort of numerically stable, right? And so if we want to get what the sum of the probabilities are, if we sum up the logs of the probability base B, we get something that is a function of the product of the probabilities. And if we really want that probability at the end, we can raise that number to the b to that number, okay? Often we just want to compare probabilities. Is one probability bigger than another? In which case the log of that probability is going to be bigger than the other, okay? So if you're multiplying large numbers of small numbers together, you're better off dealing with logs. Yes?
I'm sorry, what do you mean by the term numerically stable?
Numerically stable means that, again, we have this world, we were taught in high school there is a world of real numbers. How many bits do real numbers have in the world? They have an infinite number of bits, and we don't have to worry about it. Your computer, does it have an infinite number of bits for every real number? No, okay? So you will quickly run into problems of storing products. If you multiply large numbers of probabilities together, the answers are going to be kind of weird depending upon what how integer, not real numbers are represented in your computer. Has anyone here ever had a course in numerical analysis? A few people. In the olden days, when I was a computer science student, you took a course in numerical analysis and you learned to understand what was the error in numerical computations you would expect. After doing a certain number of computations, you had a bit precision, you had all this kind of stuff. The course was like death. It was boring, okay? But it was clearly an issue you had to worry about. And taking the logs is one way to avoid the problems of numerical error that will happen here. Any questions? A second reason we're going to use logarithms is to deal properly when we're dealing with ratios, okay? Again, I kind of showed this problem when we talked about geometric mean, okay? If I have ratios like today's price over yesterday's price, that's something you might conceivably compute in a stock series, right? You might be interested to know what's great about that. What's great about that is, what would the ratio of today's price over yesterday's price mean? Well, if the price was unchanged, it'd be 1. If the stock went up, it would be greater than 1. If the stock went down, it would be less than 1, right? This might be one way of computing something about how does the price change over time, right? Not necessarily the best way to do it, but it makes a sense of this thing. But as we noticed, if the stock had a good day where it doubled one day, and the next day had a terrible day and it got cut in half, the net result is that there has been no change. But if we, average these two, this went up by 2, this is now 1/2 of it. The average of 2.5 is not 1. Okay, ratios are kind of weird. Okay? But if you take the logs of ratios, okay, you will see that the difference, if it was a log base 2, doubling the log base 2 is 1. The log base 2 of 2 is 1. The log base 2 of 1/2 is -1. So if you take logs, you get equal displacements in ratios. And this is an important thing. Any questions about that? Okay, let me show you this by showing you something one of my students tried to foist on me. Okay? This was, we were analyzing, I think it was some electrical data, where we're showing for each of a certain number of power stations. The old power before this treatment over the power used after the treatment. Look on the left. Does anybody see the outlier points? Does everybody see this? It's plotting the ratio. Which is the outlier? Which point here is not like the others? Does anybody see something? Okay. Which one is it? Is it this? The answer is no. Okay. You're saying, wait, but it's so far away, it's got to be the outlier. Where is the outlier? Well, notice that when you have a ratio of x over y, how big can it get? It can go to infinite, right? How small can it get? It can't go minus. If it's, well, assuming both things are positive or 0, it can't get less than, it's either on one side going to be 0 to 1, and the other side 1 to infinite, right? The ratio of 1 means it stays the same. If I plot the log of these points, now where is the outlier? Okay, does everybody see these are the outlier points? Why couldn't you see this? It's because when you take the ratio, the space was kind of artificially, if you plot the actual ratio, the room for the ratios where things go down is constrained to this little bit where the other ratio is infinitely large. Does everybody see this? When we plotted in log space, what was the interesting change? My God, this thing went down by 3 logs. That's pretty amazing, right? Any questions about it? So if you give a plot of ratios and it looks like this where there's a lot of stuff on one side, you are committing some kind of a sin. Any questions about that? Okay. What other things are interesting to know about logarithms? One is, for many variables that we will deal with, they are going to be associated with power laws, and we'll talk about what they are later on. We'll talk about distributions. But sometimes the log of a variable is a better thing to deal with because the distribution is going to be better behaved than than the original value. So suppose, let's say, we have a variable of wealth, okay? And we wanted to, let's say, figure out what is the number of years of schooling a child might get as a function of parental wealth. Remember, we were dealing with I guess we had this correlation between parental wealth and how well you were going to do on your SATs or in college, right? Now, what would happen if we tried to do this study with the child of Bill Gates? Bill Gates has some kids now. They went to college. I think one went to medical school. Bright kids, right? SAT scores go between 200 and 800 in this country. What was the highest SAT score that Bill Gates' kid could get? 800, even no matter how big Rich Daddy is, right? But if you had as their variable, you're trying to predict SAT score as a function of wealth, what would happen if you had a correlation between these and you fit the best line? For Bill Gates, what's going to happen? If wealth is something that becomes a factor, you would predict that Bill Gates' kid would have an SAT score in the millions, right? Does everybody kind of see what that effect would be? Because it's kind of an out-of-range thing. When you have a variable that ranges over a weird distribution, a power law distribution, taking the log of wealth would be a much better thing. When I look at it, people in here, you guys are poor, okay? That's you. You have wealth near zero for the most part. Bill Gates is infinitely large, okay, or very large. Now, me, I am, by average, much closer to you than I am to Bill Gates. Okay, that shouldn't surprise anyone, right? But if you take a log I am kind of in the middle. I don't know exactly, I haven't done this recently or anything like that, but it should be, there's roughly the number of logs between me and you as I am between me and Bill Gates, okay? And this is good. This shows that, there is an effective wealth you could capture on a scale that makes sense if you think of it in terms of logs. Any questions about that? Okay, so power law variables, you want logs. And again, what happens when you take a log often is that you turn a skewed distribution. Here where you've got some variable, and then here's the probability of it. It's sometimes the case with something like wealth that you have a small number of people with very large things. When you hit it with a log and now plot, instead of x, you plot the log of x, the frequency distribution of the log of x is often much better behaved. Any questions about that? Yeah.
Yes, so how does this happen? What is the underlying mathematical intuition behind why this happens?
So what is the distribution of why it happens? It depends what do you think is happening? When you say why does it happen,
One thing I really notice is that the scale is reduced. So in terms of the range of values that you're taking.
okay, so one thing you may say is, why did this happen when I took the log? You might have said, well, logarithms are smaller than the original function. But that's not so interesting. Suppose instead we switch from the dollars to kilodollars. Okay, suppose I want to measure your wealth in kilodollars, right? It used to be you had $100, right? Now your wealth is 0.1 kilodollar, right? It's smaller. Is the distribution any better behaved? No. So it's not that the numbers are smaller. It's that it's a nonlinear distribution. That's what's happening here. That when you're taking the log is the number of halvings. That's what I think of a log as being, right? Having your wealth, it goes from a small number to a smaller number, but it's not a big difference because you didn't have much to start with, right? Have Bill Gates's wealth, you've really cut it down, right? Both of them have that's one log worth, right? So what's happening here to change the shape of the distribution is this is a nonlinear transform. That is what is happening, if you want to say it. Okay? Any questions? Okay. Any questions about logs or anything like that? Okay. What I'd like to do for the rest of this class is just give you talk about the homework assignment and some look ahead for the homework assignment. Okay. First of all, are there any questions about the assignment that people have from things that they were doing, ambiguities, any interesting experiences they found they wish to relate? I'm hearing no. Okay. So I'm going to talk about a couple of things, primarily about linear regression, because I asked you to use it on the, yes, question.
Sorry, so on question 3, I believe it is, you say there was 140 splits available.
Yeah.
Is that accurate? Because
Okay, so there's somebody else has asked me, I think, did I say 140 or did I say about 140? What did I say?
about 140.
Okay, what does about 140 mean? Does 140 mean 140? It means about 140, right? Okay, so some people are telling me, oh, I didn't get exactly the number I see here. Does that mean that you're wrong? Not necessarily. Does that mean you're right? Not necessarily. But under the KISS philosophy, where you're supposed to keep things, you should not be obsessing too deeply here before moving on. Once you finish and make it pass through everything, then you can go back and obsess on this issue some more, right? Does that answer your question?
Sort of.
Do you have anything else?
No,
Okay, yes.
There was a question posted on Piazza that do we have to find out reverse count splits, and you said that there weren't much reverse count splits. And
So what is a reverse stock split? Again, we like the idea that, Apple's doing so great, the number's getting so big that, that the numbers are going to get so big that to make it convenient, I'm going to take 10 of the old shares, 10 of the old shares and convert them to one of the new shares. That's a split. No. One of the new shares into 10 of the, one of the old shares into 10, no, one of the new shares, one of the old shares into 10 new shares. Okay, that's a split. Now you can imagine a world where you have a company that is doing very, very badly. Its stock price has dropped down to $1.50. Okay? This might also be inconvenient. Okay? Why is it inconvenient? Because, if you want to, again, the change in what a price can be has a certain level of quantization. Historically, in the U.S., you would say a price can't be can't change by less than a penny a share. If you're buying discrete things, right? You go to the store, okay? If you say, how much is this item? And they say it's a penny, and you say that's too much. What are they going to do? How can they cut the price? They can't cut the price because it's already, kind of at the lowest granularity in the currency, right? So sometimes if the price goes too much, they might say, take 10 of the old shares and replace it with one of the new shares. That's a reverse split. And conceivably that might have happened in the data set. I don't know for sure one way or another, but you should be able to look for it in the same way you look for anything else, right? Now certainly these things do happen. It may not happen among the good companies that you had here, okay, because they are still but you tell me, you should be the same thing you look for. Any questions? Yes?
So when plotting the correlations between the price movements of every stocks, surprisingly there was no negative correlation between any of the stock pairs.
Okay, so now what you're saying here is that you correlated and there was never a negative correlation between the prices of any two stocks, right? That the price of, of every pair of stocks, there was a positive correlation, okay? Now, is that possible? Okay. Let's think about it. Is this right or is this wrong? It is possible. Why would this be possible?
Because the question specifically asks us to find the correlation for a top N companies. Now, if our idea of picking top N companies is similar, like we want to pick companies who grew in size by a factor of more than 10, then every company would have showed a positive correlation along with time with each other as well.
Okay, what I think you're saying, and correct me if I'm wrong, is there probably are days that are good. What is it? If suppose something good in the economy happens, they announce inflation has gone down. Is that good for Apple? Probably. Is that good for every other company? Probably. So there is somewhat of an effect of there are up days and down days, and on an up day, everybody wins. Okay, a rising tide raises all boats, I think they said. So that might be one of the things you're seeing. The other question is, what exactly did you correlate?
The actual movement of stock every day, like the
So you did correlate the movements. Okay, that's what I wanted to see correlated. What would we expect the correlation between stock prices every day would be? Suppose we consider for any two prices, two stocks, and we didn't correlate the movements. What do we think the correlation for that would be? Does anyone want to give some kind of try to explain that? Does anyone have a feeling about that? If we didn't use movements, would there be anything you see over time there? Well, think about it, okay? But that's unimportant. That's not here for now. But bottom line, if you ask me about movements, they will usually say, if you listen to your stock report, they will say, today was a good day on the, 432 of the 500 of the S&P 500 were up today. Okay, they often will tell you how many went up and how many went down, and the answer is usually a much bigger. The majority is going to be much bigger than a half. Okay, so that might explain what you're talking about. Any other questions? Yeah.
I did not get the fifth part of the question.
What?
Fifth part.
What's the fifth part of the question?
Plot the distributions of frequency of daily price movements according to statistics. What type of classical distribution does it look like, and are there any surprising deviations from the theoretical?
Okay, so what is a distribution? Does everybody agree this is a distribution? Okay, there is a value on the x-axis, okay, which I think I'm hearing is price movement, okay, as you have done. And there is how often do you see these kind of price movements, right? So you should get a distribution. Does it look like this? Does it look like that? What does it look like? Why is it? Does it look like something else? Okay? What does that look like and why is that done? That's kind of what I'm interested in knowing. Okay, yeah?
What is the theoretical distribution?
Well, okay, we will talk in here about, does anyone ever heard of the normal distribution? Okay? Something like this, what do you think this is? You say that, why do you think it's a normal distribution? Well, it kind of looks like a bell. Okay? The normal distribution has a formal definition, which is stronger than kind of looks like a bell. Okay? But I think that maybe you're expecting something like this. Is that what you see? Okay? That's kind of what I'm asking you.
So we have to assume any kind of distribution.
I'm saying, look at it, see what, tell me what you learned. That's kind of what I guess I'm telling you. Okay? We agree that there's different things that could happen. What happens? Okay? Is it what you think should happen? That's the kind of thing that I'm interested in. Okay, anything else? Okay, what I'd like to talk about here is one of the things that I do ask you to do at the latter part of the assignment is to predict I believe it is earnings per share. Is that correct? Has anybody tried to do that yet? Okay, well I encourage you to try to do that. And a regression problem is one where you're trying to kind of forecast or predict a numerical value from a feature, a numerical score or a value from the feature data. Okay? And, often I would say it's a lot like curve fitting. Okay? You have a bunch of observed points. If it was only a one variable thing, you have an x variable, you got a y. Okay? You're looking to try to find the relationship between x and y. Okay? Often that kind of reduces to trying to produce a function or a curve that passes through or as close to these points as possible. Okay? Now, in one dimension, it's easy to see it as a curve-fitting thing. The world gets more complicated when you have d features. You get into a world where you're trying to predict y as a function of d variables. Okay? Any questions? Now, here, if we try to do a regression, if you look at this thing, you see a linear relationship. I do believe that you could predict y as a function of x, linear function of x. Linear function of x. Here is one where if you look at that, do you think that this is growing, y is growing as a linear function of x? Not really. It looks maybe to me more quadratic. Okay? Now, if you fit it by a line, the line would look like the thing that I have there. It's not a great fit, but it's not unbelievably terrible, okay? And linear regression is about trying to produce linear fits from the features. The good thing about linear regression is that it is simple and a good first start. And if you use it right, you can get it to do more clever things, like fit the quadratic, actually. We'll talk about that probably later, okay? But linear regression is saying find the best linear function of the features to explain the target, okay? Any questions about that? I think I mentioned the other day that I was going to a wedding of one students who met in my class, okay? And I went to this wedding, and I met somebody from Tesla, not Tesla, from the company that, Elon Musk company that's putting something in people's heads, okay, fine. And we started talking, and, you know, there was some engineering question of how do you figure out what the thing is saying, okay? And there's got to be some kind of a classifier or something that takes the signals from these electrodes and, you know, comes out with, you know, does the guy want to buy a Tesla or not, right? Or something like that. You got to try to figure out what they want done, okay, based on the signal. And so I asked them, what kind of a classifier do you use to try to build this? And, you know, they use something more complicated. But one thing that he said is that the signals are great. You know, we could even use a linear classifier, okay? And that's saying that, you know, again, it's not the best thing that you would use, and it's not the thing that's used in people's heads, but it is a sign that these linear classifiers have power, okay? So what is linear regression? We have a set of endpoints in feature space. We have a y value. We want to find the line that best approximates it. And again, this can be in many dimensions, okay? It's not, I draw it in one dimension because one is easier to draw, but of course there's no reason we can't do it in M, okay? A linear fit, what we want to do is, given the points, if we have p dimensions, we want to compute these coefficients, b0, b1, ... bp, such that that constant times 1, that's an additive term, this constant times the first variable, plus this constant times the p variable will give us that target, okay? Any questions? And the magic is that linear regression is something that people know how to solve. There are, as we'll talk about it, there's a good closed form algorithm for it. There are other algorithms to solve linear regression problems, okay? But as far as you're concerned, there is a library function that computes linear regression. Does anybody know what Python library this is in? What was it? Scikit-learn, okay? So on some level, how do you compute a linear regression? You call scikit-learn, okay? So, you know, on some level, that's not rocket science, okay? But on the other hand, building using it in the best possible way does require some thinking, okay? Why do we like linear functions? Linear functions are easy to understand, okay? They are often reasonable as a first default model, okay? Some people sneer at linear models. Oh, I want to do deep learning. I want a nonlinear, okay? But on the other hand, a lot of things happen in linear ways, okay? You know, what do we think should happen to the value of a company when its income doubles? What should happen to the stock of a company? If your stock is what a company is worth, right? If it suddenly starts making twice as much money, what do you think the value of the stock should do? Should go up. How much should it go up? Okay. Does anyone want to make a proposal? It goes up whatever people want to bid, but if you wanted to think about it rationally, it probably is going to double, right? It probably should grow something like linear from it, at least as a default. If I want an explanation, if I have, if you were going to give me $1 a week, how much is that worth to me? I'm going to say that that is worth half as much to me as if you're going to give me $2 a week, right? So if you believe that, you would expect that something like that would grow linearly. You know, if I want to think of how does your weight grow, how much as a function of how much food you eat, okay? I don't know how that works, okay? But my gut feeling is that if you eat twice as much food, you will gain twice as much weight, okay? At least as a first approximation, right? Okay, so we like linear functions. If you really want your relationship that you observe to be linear, measure it at only 2 points. Does everybody agree with that? If you measure it at 2 points, what is the best fit for it? A straight line, right? You know, hopefully you have a world where there's a real relationship, and when you see more points, you'll validate it. Okay. What else can I tell you now? Okay, so everybody should believe, what do you have? You have on the homework, you have a bunch of statistics from the balance sheets of each company. Is that right? I think that's what I asked you to do. And I'm asking you to predict the earnings per share based on the balance sheet. Okay? Now, it should be clear that if you have a matrix of statistics, the X values and the corresponding Y, you can call scikit-learn and build a model to predict it, okay? This, I hope, is clear to everybody, right? Now, if you do that, that's good. Recognize that there are other issues that could come up that might make for better regression models. As I remember, the first thing I did was ask you to use linear regression. The last part I ask you to do is try to do a little better, right? Now, how might you improve a linear regression model for estimating what you call it, let's say earnings per share? One might be, in any situation, is what happens if you remove an outlier, okay? Are there outlier points? I don't know if in your data whether there are outlier points. What would be an outlier? Okay? You know, this would be a company that's value seems to be independent of how much it's actually earning. Does anyone have a company like that in mind? What? Tesla. You're saying maybe Tesla. You could imagine a world where everybody thinks, Elon Musk has superpowers to make money. And even though Tesla's not making money now, maybe it'll make money in the future, right? So maybe there are companies where the stock price has nothing to do with the income. Should that point be removed when you try to fit it? What happens in linear regression if you try to fit it, if you have an outlier? It's going to chase the outlier, right? Should you remove it? You say yes, maybe, maybe not. Okay? You certainly can remove it. Are you justified or not justified in doing it? That is now a judgment call, right? The question is that representative or not? You might want to add nonlinear functions of the features. Suppose, let's say, remember we wanted to try to fit, we had some points like this, where this was x. And this was what happened, right? How could I use linear regression to fit this function very well? If my only feature was x, that's the best I could do, right? What other feature could I add that would make it do better? What if I also have a second feature called x squared? Right? Now, if I ask for a linear function in x and x squared, what's going to happen? Now, that's going to behave like that, right? What is the function? Y equals 2x plus 3x squared plus 1. That is a linear function in x and x squared, right? Maybe that's something you want to do. Maybe not, okay? Should it be the first thing you try? Well, KISS, keep it simple, right? You realize that sometimes you may want to scale your features. Should your features be x or should it be log x? Okay? Maybe it makes a difference, okay? What happens if you have variables that are highly correlated? What if I want to predict your weight as a function of your height in meters and your height in inches? Okay? Do we agree that we could have somebody say that a function like weight equals, some constant C1 times your height in meters plus some constant times your height in feet? Is this going to be a good model to predict somebody's weight? Say no, why not? Someone with a hand, okay? Why is this not a good thing? Yeah? You're saying that height in meters and height in feet are highly correlated? Very perfectly correlated, right? What's going to be a problem with this? Yeah? Computational resources, having two variables is not going to bring your computer to its knees. So I'm not as worried about the computational resources, but I'm more worried about the fact that this doesn't really have a unique solution to it, right? Am I better off, I could have an equally good model just using the height in meters, right? Okay? And if I demand using both of them, I split this arbitrarily, right? So weird things potentially happen when you have correlated variables, right? Is this for you to worry about first? No. Is it something that might be aware of? The other thing that I will say is, make sure that your target is linearly predictable. Understand what you're trying to compute and whether what you're trying to compute, it makes sense to do it as a linear function of what you're doing. Okay? If it doesn't make sense, maybe there is something else to compute that makes better sense. Okay? And that's the warning I'd like to give you. Any other questions about this? Okay, fair enough. So get working on this. Next class we will discuss, basically data sets and data collection and how that starts to happen. Okay, thank you.